Thank you. Okay, that's good. This works. Yeah, thank you very much for the introduction. Thank you for not giving us the danger microphone. So yeah, with that we can get started. So I'm Konstantinos. This is my colleague Niki. We are from the University of Luxembourg, and today we will present our satellite, our PocketQube, which is called POQUITO. Now, we had a presentation last year here as well. Last year we talked about a smaller class of satellites, but this year we will talk about what kind of PocketQubes we are developing in the university. So just to give you a little bit of context for those who don't remember it from last year. So we're in Luxembourg. Luxembourg is a small country in Central Europe. You can barely see the highlight on the map right there. And there is one public university in the country, basically, which is the University of Luxembourg. And it's a small university relatively, and it's a research university, so not as much teaching going on as research. And within this university, we have an interdisciplinary center where we are working on, and in this center, we're developing various computer science, information technology kind of research. So we have research about financial technology, space systems, automotive, cybersecurity, and so on. And within the space systems research, so some of you may know that Luxembourg is kind of a hub for a specific group of space activities, especially anything related to space resources and so on. And we have a master's program, so we have an interdisciplinary space master's, and we don't have a bachelor's program. And this creates kind of an interesting situation in Luxembourg, where we have a lot of companies, a lot of demand for space engineers, a lot of open positions if you're interested, but not a lot of influx. It's a small country, small university, not a lot of people are coming in, and we have a very wide gamut of students who also join our master's program as well. So what we want to do as a university is we want to teach people how to make spacecraft, and we're trying to find ways to look at the whole development life cycle, let's say, of a spacecraft from concept design to operations and verification. And this is hard to do with a CubeSat in a practical sense. And the previous talks mentioned this, that usually with PocketQubes we have this kind of simplicity, ease of construction, low cost, fast development times, which allows students and researchers to basically look through the whole mission during their stay at the university, or during like a very small period of time, without really missing any parts or looking just at the development, let's say, or just the operations. So we decided as a university, as a space systems research group, to look into this kind of concept. So small spacecraft that can be developed in a very small amount of time. And PocketQubes are the ideal platform for this. So this is what we're developing. This is POQUITO. This is a backronym, as we call it, PocketQube for In-Orbit Technology Operations. Now, last year, we came with a ChipSat concept here, so a much smaller satellite than a PocketQube. But let's say that in this conference, you convinced us to take the next step and go into the larger space object manufacturing. And we started working on this PocketQube a couple of months ago, around October, September, and we made let's say a very simple development model, which is this one. So you can see a render and some pictures on the bottom. And this is a very simple technology demonstration experiment. It's just, say, a proof of concept, something we want to fly to space and see if we can make it work, similar to what other presentations today talked about. And I will give you a very, very brief introduction about our technology and our stack. So we're not building the entire thing ourselves. It's mostly based on off-the-shelf stuff. So our design is based on the LibreSpace Foundation design, so the cubic PocketQubes that recently flew, which are also open source. So our base plate, which has the deployable UHF antennas, is based on the LibreSpace Foundation's design. The base plate is directly connected to the communications module, which is also UHF built mostly around radio amateur frequencies. And the same thing is true for the APS as well. So off-the-shelf, lithium-ion cell, a battery management power system, and some very simple solar panels. So 4 solar panels with one on each side. And for the solar panels, we did a couple of modifications that Niki will talk to you about later. And this is basically our simple platform. Now, on top of this platform, we add our own stuff. So what we are developing in-house is an ADCS for the tumbling. So you can see that we have a magnetorquer board and also the main, let's say, ADCS control and sensor board. And this thing you can also find open source online, so the designs are already up, not tested, so not guaranteed to be working, but you can, if you can make out that link on the top, and I hope we will share it with you later as well, you can actually see the PCB design of this. And we also have a ChipSat payload on the top that I will talk about later. So as a summary, we have the LibreSpace Foundation platform, and on this we are adding an ADCS that we're building in-house and a ChipSat payload on top, so basically 2 payloads. I have some more pictures here. So this is our CAD model without the solar panels on the side, and again a couple of pictures of our development model that we've built without the solar cells put on the solar panels. Now I will briefly talk about the ChipSat payload that we have on top. So a ChipSat is a very small satellite, which is smaller than a PocketQube and is flat on 1 dimension. So this is around 5 by 5 centimeter circuit board, and it's built to be something independent. So not electrically connected to the PocketQube. It has its own communications and its own power generation. So you can see the solar cells on top. And for this, we want to do an intra-satellite communication experiment. So we have an optical link instead of a radio frequency link. And what this does is that we have the ChipSat on top, and the ChipSat communicates with the PocketQube through an LED diode. So ChipSat produces light, and then the PocketQube receives the light through a photodiode and decodes the information in there. Very similar to the experiment we had last year, for those of you who remember it. The design of the ChipSat is, again, something very simple. So we have a microcontroller with some power supply, a couple of sensors, so a magnetorquer light sensor, a couple of infrared cameras as well. And in the center, we have an LED, a very small LED that basically blinks, follows a specific encoding modulation pattern, and transmits all the generated data back to the PocketQube. Now, the reason that we want to do a ChipSat is that also as a research group, from a research point of view, there are some interesting applications for ChipSats. There are applications, for example, for independent beacons for larger satellites. ChipSats can work as escort spacecraft. We can do some interesting planetary science with them. An interesting concept would be to just have a ChipSat take a selfie of your satellite if you do maybe some kind of formation flying. You can experiment with weird and niche concepts like distributed or fractionated spacecraft. And ChipSats are an interesting, a very niche concept that we actually want to test to test and experiment with in the university. And we found out that the PocketQube form factor is a very easy and very convenient form factor to actually test those kind of ChipSat payloads, ChipSat spacecraft, because the deployment opportunities exist, the launch opportunities exist, so we can just take the PocketQube form factor, put our payload, put a ChipSat on top, fly the entire thing, and see how our ChipSat works. So for the next part of the presentation, we'll talk about our second payload, which is the ADCS, and for that we have Niki here with us, so let's go ahead.
So we all know ADCS is an important and complicated part of any satellite, but the complexity is really depends on the type of mission we want to do. So the usual way of design, simulation, and implementation of ADCS is to go step by step. So the first step is statistical design. We usually do research to find different developed methods, algorithms, and hardware to find the best solution for our mission. So the next phase is usually model-in-the-loop simulation, which means we want to simulate and model the whole system, the entire mission for ADCS, and I will talk about it later. And then we take out the real processor we want to put on a satellite, and we still have the simulated model of sensors, actuators, the environment, and other things in the computer, and we make a loop between the computer and also the real processor we want to have on our satellite. And the next one is hardware in the loop. So it means we have all the components out of the computer, and we connect them, and we run a test in a specific test bed, which can be an air-bearing test bed with a Helmholtz cage or a different kind of test bed. So the first phase for us was statistical design. So I had some experiences with working on ADCS, but my experience was usually working on microsatellites and CubeSats, and the smallest satellite I've been involved in was a 3U CubeSat. So when I joined the University of Luxembourg, I realized that they were working on sub-CubeSats, and this 1P PocketQube was 24 times smaller than my previous experience. So I realized that there is no space inside this to do a traditional way of ADCS, which is putting reaction wheels and magnetorquers, because the space is so small. So I started searching different missions that have been deployed. I searched on this website, and you can filter the satellites, filter the list by the size of the satellites. So for example, if you see the PocketQubes, 1P PocketQubes, you can now find 63 records, but here there are many missions that are planned to be launched. So for example, you can find our mission here as well. Many of them are not launched yet. Many of them had some failures, and there are around 2 or 3 of these having active ADCS on them. But we found another thing, which is a gap between academia and industry. So many industrial projects having ADCS don't really publish anything about the details, like the documents or papers, but we can find many papers in academia, but they're very theoretical, and they don't launch it for real, or we cannot see any result of those papers in space. So we had to design everything from scratch, and we had this model-in-the-loop simulation. So we modeled everything after defining the requirements and selecting components and finding the sequence, the modes we want to have in our ADCS. And after calculating disturbances, we simulated everything, like the dynamics of our PocketQube, disturbances, sensors, actuators, and also ADCS algorithms. So for our mission, we really didn't want to make it super complicated. So we didn't go through the nadir pointing mode, and we just wanted to do something for the tumbling. So this is the control mode sequence we have. We have the initial detumbling, then we have antenna deployment. So because of the produced torque, we'll go to the second detumbling mode. So this is the result of our simulation, and we have a 3-axis control. The accuracy is around 2 degrees per second. And we have power optimization, so we worked a lot on this part. We ran the algorithm a lot, and we changed different parameters to make it optimized. Also, we could calculate the required magnetic dipole moment for magnetorquers because we wanted to make them from scratch. This is the hardware development part. So after MIL, we moved to PIL, but we didn't have the processor to take it out. So we had to create our own processor and the whole ADCS board. So on this PCB, we have a microcontroller, we have IMU, which is a 9-axis IMU, 3-axis gyro, 3-axis magnetometer, and 3-axis accelerometer. And also, we have a spare magnetometer because this sensor was super important for the tumbling. So we have a spare model of that. Also, we have 4 sun sensors. They're not on the PCB. They'll be outside, but we have connections for them here. And this is our magnetorquer. So we merged the printed coil with our solar panels. So it doesn't take up any space. So this is the kind of modification we did on the solar panels on the board. And also we have a separate magnetorquer for Z-axis. So these are 4-layer coils. Each layer has 54 turns. And also this is a summary of ADCS. The total mass of the PocketQube for us is around 216 grams. And for ADCS, it's around 20 grams. So the average power consumption, okay, this is the video. The average power consumption is around 30 milliwatts, but we have a peak when we deploy antenna. So the peak goes to 380 milliwatts, but we have seen this in our design. So this is the result of the tumbling mode. On the left side, you see the satellite before the tumbling, and the right side, you see after the tumbling.
Yeah, I think that's my cue. Yeah, so all in all, as a summary, we are expecting to launch this thing next year, 2024. We have already signed a contract with Alba Orbital, which is already public. And right now, the current status of the project is that we are doing some design iterations, and by design iterations, I mean we're actually building models that we try to have them integrated, interfaced, and operating. So we almost have V0 made. Now we're working on version 1. And just a couple of key takeaways that we had so far. So first of all, we've had a lot of, let's say, fun exploring the legal and regulatory aspects of the mission. This might be something which is specific to Luxembourg as a country, but we really needed to spend a lot of effort to go through all the legal requirements of registration and frequency authorization, and also insurance. And in the end, we found out that the cost to actually insure the mission as required by our laws might be much higher than the cost of the PocketQube itself, including all design iterations. And this is something interesting. So if you've also had troubles like this, especially from an insurance point of view, please talk to us, because this is something very new for us, and we are really spending a lot of effort on it that we would not like to spend. And finally, another key point that's not very visible, very faintly written there, is that we are following a very iterative approach, and we are building a lot of things hands-on, even with a very limited team size in terms of how members we have. This is something that was extremely useful to us, and I've seen many other teams do that already from today's presentations. And I'm hearing numbers like we're developing missions in less than 1 year, and this is something great. This is something that's really possible. Not very possible with CubeSats, especially if you are a university or a high school or someone who's up and coming. And really, this has been very useful for us, especially if we're a research group where we have to split our time between our research and our development project. So one key takeaway from this is that this kind of approach seems to be working. So yeah, this is our last slide. You can see it says last slide. So thank you very much for your attention, our contact details, and we will be happy to take any questions. Thank you very much.
Question from Timur?
Thank you very much. So can you please go back to that slide where you show the coil itself?
Is it? No. This one?
Yeah.
Yeah.
Can you point out the actual coil? Because it might be faint, but I imagine it's the central square light.
Yeah, this one is the real picture.
Yeah.
So this is the panel we have for solar cell, but this one is the coil. It's integrated.
Right.
So it's merged.
Is it a 3-axis? This is one axis, of course.
Yeah.
Do you have 2 other axes as well?
Yeah. We have 2 panels, 2 lateral panels, And then one is this one. This is for Z-axis.
I see.
So it's inside the cells.
Great, thanks. Any other questions? No? Okay, cool. So we want to our next talks.
Thank you very much.